We are in Chapter 1, Section 1, where we are discussing the background to mechanics of materials. We are in the fourth session. Previously, we have discussed action-reaction forces and free body diagrams. We have also discussed the method of joints in plane trusses and the method of members in plane frames. Here we discuss the method of sections in plane trusses. This again is a roadmap of the first 4 chapters, which has 36 sessions. We are in session 4, which is the last session of the background. At the end of the session, we give a brief summary of section 1. Here we discuss method of sections. We have earlier discussed plane trusses and the method of joints. Using the method of joints, we could find out the forces in the members of the truss. Similarly, using method of sections, we would be able to find out the forces in members of the truss. Our method of sections is quite important since it is used in other members as well. So we will see the use of method of sections in quite a few different chapters. Now consider a rope AP, which is subjected to a tension P. Let C be a point in the rope. Now, if we cut the rope at C and insert a spring scale, then the spring scale will show a tension P. AL here is pulling the spring scale with tension P, and the spring scale is pulling AL with a tension T. RB is pulling the spring scale with a tension T, and the spring scale is pulling RB with a tension P. Now, instead of the spring scale, let us consider that a thin joint inserted at C. Then AC will pull the thin joint with tension T, and the thin joint will pull AC with tension T. Similarly, CB will pull the thin joint with tension T, and the thin joint will pull CB with tension T. Now consider C or the thin joint at C to be part of the rope itself. Then AC will pull CB with tension T, and CB will pull AC with tension P. Or in other words, we can say that AC is in equilibrium due to the external force applied at A and due to a force applied by CB at C. And CB is in equilibrium due to a force P applied at B and a force due to AC applied at C. So AC is in equilibrium under an external force and an internal force due to CB. And CB is in equilibrium under an external force and an internal force due to AC. Earlier we discussed that if we have a whole rope subjected to tension T, and then we take an imaginary section at C, then there will be two forces acting at the imaginary section. These two forces are equal, opposite, and collinear. So they form an action-reaction pair. C can be any point in the rope. We can extend this idea to more complicated structures, such as a plane truss. So we can take a section such as HH, cutting the plane truss. To start analysis with a truss like this, first of all we look at the whole truss and find out the reactions. So we can take moments about B and find out the reaction at A. And then we can sum up forces in vertical and horizontal directions to find out RPX and RPY. We then take these sections through three members. As earlier discussed, the left-hand portion will be in equilibrium under external forces and these three internal forces. Similarly, the right-hand portion also will be in equilibrium. Knowing the external forces and the reaction, and using the three equations of equilibrium, if we consider the left-hand portion, we can find out the three unknowns. It's the forces in the three bars. We can do the same exercise with the right portion. The forces, if we start with the right portion, the forces that we get will be the equal as the forces in the left portion. Here the force 1 and here the force 1 form an action-reaction pair. So to the forces 2 and 3. We start looking at problems involving trusses. So this is a symmetrical truss, as you can see. The height here is given as h. There are 6 bays, each of dimension A. There are 5 forces, each of magnitude B. And the forces are also symmetrical. The reaction at A would be 5p by 2 due to symmetry, and the reaction at B would be 5p by 2 due to symmetry. In problems using method of sections, we may need to take one section or more than one section. Here we need to find the force in R1, 2 and 3. We know all the external forces acting and the reactions acting, and we take a section as shown. We isolate the left portion and consider its equilibrium. So we know all the external forces acting on the left portion, and you find the forces in the three bars. As we can see, we need to find one vertical forces and two horizontal forces. To find the vertical force in bar DE, we can sum up all the vertical forces. So we know these forces and as well as RA. So we can find the force in bar DE. Next, we take moment about D. Both these two bars pass through D. So the force in bar CE will cause a moment about D, as will the force P and RA. From that we can find the force in CE. Next we consider forces in the horizontal direction which add up to 0. So there are two forces, force in CE and the force in DF. So the force in DF would be the opposite of force in CE. Here we consider another example. So this is a truss attached to the wall, and there's a force P acting at A. The dimensions are given. This height is 100 millimeter. These are 50. C is 75, and AC is also 50. Here we are required to find out forces in BD, in CT, and EF. We'll solve the problem by taking two sections. The first section is taken here. So we'll consider the equilibrium of this portion. We notice that we don't need to find overall reaction forces of the truss in this problem, and we are proceeding from the right. So considering equilibrium of this whole portion, see that the forces that are acting downwards are the force in the bar PC and P. So summing of forces in the vertical direction, we can find the force in bar PC. Next, if we take moment about C, then both AC and BC is passing through point C. And then BD will cause a moment about C, and P will cause a moment about C, from which we can find the force in BD. Now, BD and AC, forces in the bar BD and AC are the only forces in the horizontal direction. So summing of force in the horizontal direction, we already know the force in BD. Then we can find the force in AC. We take a second section through the two bars we have already considered, so AC and BC. And through the bars we need to consider, that is CT and EF. So this is the section. So we'll consider the equilibrium of this section and find the forces in the two other bars that we are required to find. To start with, we find this angle theta. And now this is 100 and this is 75. So tan theta is 100 by 75 is 1.33, from which we find theta as 53.123 degrees. Once we found theta, we'll find out the perpendicular distance from E to the bar CD. Can use this triangle. So we know theta, and we'll find out x. So sine theta is x by 75, from which we find out x or this distance as 60 millimeter. Now we know the forces in AC and BC, and the point E passes through the other two bars, EF and EG. So if we take a moment about E, we would be able to find out the force in CT. This force also passes through point E. So if we take moment about E, then there's a force due to CT that causes a moment, and this force P which causes a moment, from which we find the force in CT. If we take the horizontal forces, then the force in CD cos theta plus P by 2 plus the force in EF would be 0. So summing up the horizontal forces, we can find the force in EF. So I've been able to find out the force in the 3 bars that we wanted to. We have looked at 2 trusses now, and we can make a comment that depending upon the truss and depending upon where we need to find out the forces, we should make judicious choices of the sections taken. Also, we can make judicious choices of where to consider moment. This will allow us to reduce the workload. So here we take another example. This truss is symmetrical. This dimension is 75 and all the bays are 50. Loading is also symmetrical. And the reaction at A and M will be P. We are required to find the force in BD and EG. And we'll take a section as shown here and consider equilibrium of the left portion of the truss. So here we have taken the left portion of the truss. Now in the method of the joints, we saw that if bars and force are collinear, then the magnitude remains the same. So the force in CD will also be P here. We can take moment about point E because EF and EG passes through point E. Then we are left with only 2 forces that causes moment about point E. So that is the force in BD and the reaction at A. So from which we can find out the force in BD. Now summing up all the horizontal forces, we see that the force in BD and the force in EG are the only 2 horizontal forces, so we can find the force in EG. And summing up the vertical forces, we see that the force acting in EF would also be P. Here we have a more involved truss problem that we can solve using the method of sections. APC is an equilateral triangle. A force P acts at F, and the force P acts in a manner so that it bisects AC. As such, the reactions at A and C will both be P by 2. The angles FCA, BAB, and CPE are all 15 degrees. We need to find out the forces in AC, AB, BC, CF, AD, and BE. One way to start solving the problem is to take a section here and take another section here. Consider a section here. Then resolving forces in the vertical direction will get a relation between the force in AB and AD. And resolving the forces in the horizontal direction will get the force in AB and AD in terms of the force in AC. Similarly, with this section, Resolving forces in the vertical direction will get a relation between the forces in BC and CF. And resolving forces in the horizontal direction will get the force in BC and CF in terms of the force in AC. Here we have shown the section AA, and we'll find out the force in AB and AD in terms of the force in AC. So we consider the left hand portion of this section, and considering equilibrium, if we solve the forces in the vertical direction, then we get F1 cos 30 plus F2 cos 45 plus 0.5 P is equal to 0. Solving forces in the horizontal direction, we get F1 cos 60, F2 cos 45 plus F3 is equal to 0. Substituting the cost values in these two equations, we get equation 1 and equation 2. You notice that the coefficient before F2 in both equations 1 and 2 are the same. So to solve these two simultaneous equations, we multiply equation 2 by -1, as we can see here. We get a relation of F1 in terms of F3 and P. Now substituting this value of F1 in equation 1, we get F2 in terms of F3 and P. Let us now look at section BP. We consider equilibrium of the right-hand portion. Consider forces in the vertical direction. F4 cos 30 plus F5 cos 75 plus P by 2 is equal to 0. Considering equilibrium of forces in the horizontal direction, we see that F4 cos 60 plus F5 cos 15 plus F3 is equal to 0. Substituting the cost values, we get equation 3 and equation 4. In equation 4, to get the same value of the coefficient of F4 as equation 3, but opposite in sign, we multiply by minus 1.732. Solving the simultaneous equations, we get F5 in terms of F3 and P. Now we have obtained F5 and we put it back in equation 3. Then we get F4 in terms of F3 and P. So now we have got the forces in four members, AB, AD, BC and CF in terms of the force in AC, which has been designated as F3. Here we take a section CC as shown to solve the problem. Unlike the other two cases, we consider equilibrium of the bottom portion. There's no net external forces acting on the bottom portion since there's a load P here, but there's two loads P by 2 acting in the opposite direction. There is a force in bar AB and bar BC and bar PE. We know the force in bar AB in terms of the force in AC and P, and we know force in bar BC in terms of the force in AC and P. However, we do not know the force in BE. We can resolve these three forces in the vertical direction and obtain the force in BE in terms of the force in AC and P. The force in AC has been designated as F3. We can then resolve the forces acting on this section in the horizontal direction and obtain a relationship between F3 and P. So here the forces are shown, and we first resolve the forces in the vertical direction. So F1 cos 30 plus F4 cos 30 plus F6 cos 15 is equal to 0. Now we know F1 in terms of F3 and P, and we know F4 in terms of F3 and P. Now substituting the cos values and F1 and F4 in this equation, we find out F6 in terms of P and F3. We then resolve forces in the horizontal direction. Then F1 cos 60 minus F4 cos 60 minus F6 cos 75 is equal to 0. Now we know F1, F4 and F6 in terms of F3 and P. We substitute all these values in this equation to obtain a relation between F3 and P, from which we get F3 is equal to 0.43 P. Now F3 is the force in AC, so FAC is equal to 0.43 P. We had earlier obtained F1, F2, F4, F5 and F6 in terms of F3 and P. So substituting the value of F3, we now get F1, F2, F4, F5 and F6 in terms of P only. We can do a check. Say F1 is minus 0.191 P, so it acts towards the joint A, and F2 is minus 0.473 P, so it also acts towards the joint A. Resolving these two forces in the vertical direction, we find that the force acting downwards is 0.5 P, but there's also a reaction force acting upwards of 0.5 P magnitude. Hence, our results should be correct. We have thus solved this problem using three different sections. Here we'll summarize section 1 mainly in terms of action-reaction forces. We discussed this case at the start. This is a block attached to a rope and pulled by a hand. The block does not move. We discussed two action-reaction sets. So the hand pulls the rope pulls the hand, and the rope pulls the block, and the block pulls the rope. Consider equilibrium. We do not consider the forces that the body itself exerts on the environment. So in the case of the rope, we do not consider FR1 and FR2, and the only forces considered are FH and FM. Now let us look at the method of joints. To start with, we find out the external forces in a truss. Then we consider the equilibrium of a joint such as joint A. Using the equilibrium equations, we can find out the force that acts at the joint A due to the bar AC and due to the bar AD. Due to action-reaction pairs, the joint A will cause equal and opposite force in AC and AD. So in this manner, we get the forces in the members. Plane frames are solved by considering equilibrium of the bars. Initially, we looked at the forces exchanged between the bars and the pins. So let us consider the pin at B. Now due to the bar DP, there will be force acting on the pin. The pin will react with an equal and opposite force. Similarly, there will be force acting on the pin due to ACP, and the pin at P will react with an equal and opposite force. So there are two sets of action-reaction forces at pin B. In the nomenclature used in frames, we say that DB will cause an action force and ACP a reaction force. This nomenclature is different from the action-reaction pairs mentioned in Newtonian terms. Now let us look at the pin at C. The pin at C is subjected to a force due to the bar ECD and due to the bar ACP. The force due to the bar ECD is given here as FECD, and the force due to the bar ACP is given here as FACP. Since the pin at C is in equilibrium, these two forces are equal and opposite to each other. However, we solve frames using the equilibrium of the members. So we'll look at the forces that are exerted on the members. The pin will exert a force F dash ECT on the bar ECT, where F dash ECT is equal and opposite to F ECT. The pin will also exert a force F dash ACP on ACP, where F dash ACP is equal and opposite to F ACP. These two forces being equal and opposite, F dash ECT will be equal and opposite to F dash ACP. We do not know the direction and the magnitude of F dash ECT to start with, and we represent the force arbitrarily by taking RCY and RCX in any direction we choose. However, we know that F dash ACP will be equal and opposite to F dash ECT. So once we have chosen the direction in say ECT, the direction in ACP will be equal and opposite. So here RCY is acting upwards, here RCY is acting downwards, and same with RCX. So this is the way we represent the forces at the joints, and using equilibrium of the members, we can find out all the forces that act on the members and on the frame as a whole. Now look at the method of sections. Here we have a rope subjected to a tension P. Let C be a point within the rope and we take an imaginary section at C. Then an action-reaction pair will act at C. AC will be in equilibrium due to the external force and the force due to Cp, while Cp will be in equilibrium due to an external force and a force due to AC. This idea can be extended to more complex structures such as a truss. With a truss such as this, we can find out the external forces acting on the truss to start with. Then, if we take an imaginary section at HH, there are action-reaction sets acting in bar 1, 2, and 3. If we separate the left-hand portion, then the left-hand portion is in equilibrium under external forces and these forces in bar 1, 2, and 3. Using the three equations of equilibrium, we can find the forces in bar 1, 2, and